Okay, so let me start now. So I'm going to start by just stating the Brumer-Stark conjecture and telling you some of our work about it. So the setup for this is we start with a totally real field, which we denote by F, and a finite Galois extension that is a CM field. And in this lecture series, we'll always assume that this finite Galois group, which we denote by G, is an abelian group. Okay. And we let S denote the set of infinite places and ramified places in this extension. And T will be some other finite set of places that's disjoint from S. And when you have this data, we have what is called the S depleted T smoothed L function associated to any character chi of the Galois group. So here it's not stated what chi is, but chi is just some character of G, so one-dimensional character, so a group homomorphism from G to C star. Then we associate an L function to it, which is given by an infinite Euler product. And the only difference here from what you see usually is just this notions of depletion and smoothing. So we only take the Euler product over P not in S. Notice that since S contains all the ramified places, chi of P is well defined for every P not in S. So this is a well-defined number. And then there's this smoothing operation. So just an example of what the smoothing operation does is if chi is a trivial character, then this cancels the pole of the zeta function at S equals 1, right? When S equals 1, this is just 0 if chi is a trivial character. And in general, it has a similar kind of behavior. It sort of cancels the denominators at the values at some critical values in a way, and I'll say something more about that later. There has to be some condition on T in order for this to really cancel the denominators, and particularly it has to be non-empty, but we'll not get into those conditions. There are some conditions. Now we fix a prime ideal. So there's a finite prime of F and a prime, which is sort of Gothic P, capital Gothic P of H that lives above it. And perhaps I want to say that I assume that this little p splits completely in H, even though it's not written here on this slide. Then you have the following conjecture, which is often called the Brumer-Stark conjecture, which is in this form, it was stated by Tate. Okay, so let me say, assume p splits completely in H. Okay, though I guess you could just replace H by, the maximal subfield in which P does split completely, and you'd have the same conjecture. So it's not really that important of an assumption. Then there exists an element which is a P unit in the upstairs field H, such that its absolute value 1 under each complex embedding, and such that the value at 0 of this STL function that I defined in the previous slide is given as the sort of chi weighted or chi inverse weighted linear combination of the p-adic valuations of all the conjugates of U. And this holds for all characters chi of G. Now the left-hand side of this equation depends on T in some way, and so the unit U has to depend in some way also on T. And the condition there is U is congruent to 1 modulo all the prime ideals living above those in T. Okay, so that's this condition here. I should mention this is, you might ask, what's the purpose of the smoothing set, the T smoothing, why you need it? And so this is clearly an algebraic integer, right? It's a linear combination of roots of unity with integers. And so you would have to have the left side be an algebraic integer for this to even make sense. And sort of that's the function of the T smoothing, is that if T satisfies certain conditions that I said I'm not going to state, then this actually is known to be an algebraic integer. So there's at least a plausible conjecture in that setting. Okay, so this is kind of interesting because these L functions can be computed kind of just knowing the ground field F, but somehow it's telling you the existence of units in the upstairs field H, which you might not know how to construct even, using data that's sort of intrinsic to F. Okay, so I just want to talk about some of the people whose work led to the statement of this conjecture. So really, the story starts back in the late 19th century with STICKELBERGER, who basically calculated the p-adic valuation of Gauss sums, and you can interpret his work in the language of the conjecture on the previous slide. That is, the Gauss sums, when the ground field is Q, will live in cyclotomic extensions. So, and that's the case where your F is just Q and your H is a cyclotomic extension, or maybe the maximal subfield of the cyclotomic extension in which P splits completely. And the U in that case is just a specific Gauss sum that you can write down. And so you're asking, what is the p-adic valuation of that? And STICKELBERGER calculated that p-adic valuation. And it turns out if you take the corresponding linear combination weighted by a character chi or chi inverse, then you precisely get sort of well-known formulas for the L functions of these characters of cyclotomic fields. So STICKELBERGER's theorem in this context is kind of leading you to see that maybe something like this should be true in general. And that's what Brumer conjectured. So fast forward to the 1960s, he conjectured that there should exist units or p units for arbitrary CM abelian extensions of totally real fields that play the role of STICKELBERGER's Gauss sums. Okay. Meanwhile, in the 70s, Stark was stating conjectures on the special values of L functions and relating them, or the values of their derivatives to logarithms of units. So not p units, but honest units in these same abelian extensions H, or even more general settings than the setting for this conjecture. Sort of leading terms of L functions at zero related to logarithms of absolute values of units. And Tate kind of realized that if you replaced in Stark's conjectures the infinite place, so an Archimedean place, with a finite place, then you just recover Brumer's conjecture, some form of Brumer's conjecture. And so Tate kind of imported an additional feature from Stark's conjecture, which was this condition that U is congruent to 1 modulo all the primes above those lying in T, and said that, well, that same condition should hold in Brumer's setup also. And that was kind of added to the conjecture, and that's why it became known as the Brumer-Stark conjecture. So the work of a lot of mathematicians that went into the statement of this conjecture. So the theorem that I want to state today is that Brumer-Stark conjecture, we almost know it to be true. So we know it to be true away from the localization at 2. That is, the Brumer-Stark conjecture predicts the existence of a unit in the p unit group, and we know that there exists a unit or an element in the p unit group tensor with z bracket 1/2 that satisfies the conditions of the Brumer-Stark conjecture. I should mention that if you tensored with Q, so you didn't just invert 2, you inverted all the primes, then the Brumer-Stark conjecture is essentially trivial just because of the Dirichlet unit theorem. That was, we know the structure of the unit group when you tensor with Q as a representation of this Galois group G. And so it's not too hard then when you just from basic representation theory to show that there has to be an element in the unit group tensor Q that satisfies these conditions. The p-adic valuation in that context gives an isomorphism between the unit group tensored with Q with a much simpler group tensored with Q, and you can sort of see that there exists an element in that space satisfying the conditions you want. So in the congruence conditions, that prime sub T sort of goes away if you tensor with Q. So so somehow everything about the Brumer-Stark conjecture is simple once you tensor with Q. So our work is basically, an integral statement at all primes P that are odd. And what we're missing is the integral statement at the prime 2, and that's of course something that we're working on now. I just want to mention as I move forward that there's a higher rank version of the Brumer-Stark conjecture. So I've talked about the existence of one unit, related to these L functions. When you have one prime P that splits completely, there's a conjecture due to Rubin, which says if you have R primes P that split completely, then there should be kind of R units. So, and there's, more fancy kind of, still a regulator. It's still, made out of p-adic valuations, but somehow there's a higher rank version, and we obtained that one also when you tensor with z bracket 1/2. Okay, So now let me say a little bit more about this integrality statement. So there's some conditions on the set T I mentioned. So these conditions, for example, are satisfied if T contains two primes of different residue characteristic. Okay, so as long as the size of the residue fields at these two primes are relatively prime to one another, then your set T automatically satisfies the condition. So let's just assume that maybe. Then under that assumption, there exists a unique element of the integral group ring such that its image under every character chi is equal to the value that sort of shows up in the Brumer-Stark conjecture, the value of the L function at 0. There's 2 points I should have maybe made earlier about this L function. So one is, I define this L function by an infinite Euler product, but of course that convert is only for real part of S greater than 1. So there's a process of analytic continuation required to evaluate it at 0. Okay, so you need to do some work to even make sense of the right side of this equation. I should have mentioned that when I first defined the L function. And the second fact is that, okay, well, there's clearly an element of the complex group ring that satisfies this condition. If I said C bracket G rather than Z bracket G, then, well, C bracket G just breaks up into a product of copies of C indexed by the characters chi. So you can put whatever complex numbers you want on the right side of this equation, and there would exist a unique theta that satisfies this equality. So the depth of this conjecture is not just the existence of an element in a group ring, but the fact that it's in the integral group ring. That is that when you do that, when you write down the unique element of C bracket G satisfying this equality, that the coefficients are actually in Z. Now, the fact that the coefficients are in Q, and that's true even without this T smoothing, that is an older result due to Siegel and Klingen, and there was an independent proof given by Shintani. Now, the integral refinement of that, where once you include the T smoothing, you actually get integrality, you get Z, that was done in independent work of Kasunogis and Deligne-Ribet. So this theorem itself on this slide has a very deep and rich history. And this perspective of the integral group rings gives us a nice new way to think about what the Brumer-Stark conjecture is stating. So I want to discuss that now. So I'm going to define a T-smooth class group. So this is just the usual class group, except it's modified in a certain way. It's kind of a ray class group to incorporate the set T. So the usual class group is a group of fractional ideals of H, which I denote I of H, modulo the subgroup of principal ideals. Now, if you only mod out by the subgroup generated by elements that are congruent to 1 modulo all the primes above those in T, then you get what I call the T-smooth class group. Okay, so that's the class group that shows up here. And this is a G module. That is, this has an action of the Galois group on it, because the Galois group clearly acts on fractional ideals of H, and it preserves this subgroup of things congruent to 1 mod T, because I'm looking at all the primes above T, so this is stable under Galois. Okay, so this has the natural action of a G module. And the Brumer-Stark conjecture from this perspective states something much more down to earth, which just states that the group ring element theta that I defined before annihilates this T-smooth class group. So maybe I should say something about that. Why is that true? I mean, basically, if I take my Gothic P and I hit it by theta, okay, and what does this mean? Okay, I should say what this even means. If I write theta as a group ring element, sum of AG times G, which is a group ring element, then this is just defined to be the product of sigma of product of AG. So this is just some fractional ideal. Okay, so that's some fractional ideal. And the Brumer-Stark conjecture says that it annihilates it within the class group. So what that means is that this should, if it's annihilated inside here, that means that this as an ideal should be principal. It should be, in what I'm questioning out by. So it should be principal and generated by some U that's congruent to 1 mod T. And then that U, this is the Brumer-Stark unit. Okay. Now, the only subtlety here is the issue that your U should have complex absolute value 1 at every place, and this is almost guaranteed to be true, but not quite. So there's a little bit of So the Brumer-Stark conjecture, as I stated before, is slightly stronger at p equals 2, but everything in this work is going to be, 2 is going to be inverted. So for the purposes of this talk, I mean, the Brumer-Stark conjecture is really equivalent to the statement that theta annihilates the class group, at least if you look away from 2. So you might ask how you can prove this. All right, so you want to prove that theta annihilates. So you have a G module and you want to show that the certain element that you have, Z bracket G, annihilates this G module. And you can do that prime by prime. Okay, so you can prove that if you can prove that if after you tensor with ZP, you get annihilation over ZP bracket G for all primes P, then you've proven the result that you're looking for, that over Z it annihilates it. Okay, and the punchline is that Mahesh and I can prove this for all odd primes P right now. Now, it turns out, and this is crucial to our proof, that certain refinements of the Brumer-Stark conjecture, so this, this conjecture I stated is that theta annihilates this T class group, certain refinements of the conjecture are essential for proof, because it turns out that it seems hard to prove something directly about the annihilator. The annihilator doesn't have very nice functorial properties. It's not stable with respect to base change. So, and other sort of properties like this. So it's nicer to work with another invariant of a module associated to a commutative ring, a finally presented module, which is called the fitting ideal rather than the annihilator ideal. Okay. And for that reason, I want to define what the fitting ideal is, because that's going to show up as a refinement of this Brumer-Stark conjecture. And that refinement is essential because we kind of need to prove the stronger statement in order to get this one. Okay, so what is a fitting ideal? Let me define it. So let's say you have a commutative ring and a finally presented module over that ring. So you choose some finite presentation. So finally presented means this. It means that there's a that there's an exact sequence that looks like this, where m and n are positive integers, so they're not infinity. So what does it mean? It means m is finally generated, and then you have finally many relations amongst those generators. So if R is Noetherian, it just means that M is finally generated. Okay, and once you have that presentation, then you can define the fitting ideal to be the ideal of your ring generated by all m by m minors of the matrix or representing the map F. Okay, so M is the number of generators here. So M is this M, okay, number of generators, okay. And just to give you kind of, an example, if n is equal to m, then this F is given by a square matrix, right? Because from R to the M to R to the M, and then you're looking at one matrix and you're just asking for the determinant for that one matrix. And in that case, the fitting ideal is principal, and it's just generated by that one determinant for that one matrix. And in that case, you say that M is quadratically presented. Okay. And so since this may be the first time that many of you are seeing fitting ideal, I just want to give some exercises. You can kind of look back on this slide and go back and try to prove these for yourself as sort of getting your feet wet when thinking about fitting ideals. So the fitting ideal of the quotient of R is just given by the ideal that you're modding out by. And this is really important for us, and why I said that it's a refinement, why the refinements of the Brumer-Stark conjecture related to fitting ideals is that the fitting ideal is always contained within the annihilator. So if you can show something is in the fitting ideal, then it's in the annihilator. Okay, but as we'll see lower down on this slide, the fitting ideal has nicer functorial properties than the annihilator does. Just as another important example is to think about what does fitting ideal mean. Fitting ideal is a notion of size. It's a sort of more robust notion of size than just the numerical size. It's a generalization for an arbitrary module. If you're dealing with Z, right, a finally generated Z module is just a finally generated abelian group. In that case, the fitting ideal is 0 if M is infinite, and it's the ideal generated by the size if M is finite. Okay, so that's a nice exercise to prove that. So you can see sort of in general the difference between fitting ideal and annihilator. If I have finite abelian group, so it's a product of Z mod. So there's sort of a rational, what is it called? Elementary divisor form. You can write it as a product of Z mod DIs, where D1 divides D2 divides D3 dot 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 divides Dn, then the fitting ideal is generated by the size of that group, which is the product of D1 through Dn. And the annihilator is generated by the exponent of that group, which is just the largest Dn. Okay, or if you put in this canonical form where D1 divides D2 divides D3 all the way up to Dn, then Dn, the largest one, is the exponent. That's the generator of the annihilator ideal, and the fitting ideal is generated by the product, which is the size D1 through Dn. So that gives you a sense of what these kind of mean in general, and you can see that in the case the fitting ideal is contained right in the annihilator, because Dn divides the product of D1 through Dn. Okay, so you can sort of get a sample of these first three kind of properties of fitting ideals. And the fourth property is really important, which is that if you have a surjective map of modules, then you have a containment of the corresponding fitting ideals. Okay, I mean, again, if you think of fitting ideals being some sort of generalization of size, it makes sense. If M surjects onto M prime, then M is at least as big as M prime. So the fitting ideal of M is sort of contained in the fitting ideal of M prime. And finally, this is an important property that I alluded to earlier, that it's respects space change. So somehow if you have an R algebra S and you tensor up from R to S, then the fitting ideal over S is just generated by the fitting ideal over R. And this is actually very easy if you just look at the definition. Okay. One thing I should have said about the definition, and maybe this should have been exercise 0, is that the fitting ideal doesn't depend on the choice of presentation you made. So I said you have a module M, you choose a finite presentation of it, and you look at all the minors, blah, blah, blah. But you might ask, if I took a different presentation of the same module, do I get the same ideal? And the answer is yes. And that's maybe should have been exercise 0, that it doesn't depend on the choice of presentation. All right, so now what I'm going to do is state some refinements of the Brumer-Stark conjecture. And first, let me project to the minus side. So what does that mean? Well, this H is a CM extension of F. There's a unique complex conjugation in the Galois group of H over F, so let's call that C. And then when I talk about the minus side, what I'm doing is I'm taking the quotient on which complex conjugation acts by -1. So ZP bracket G minus, the minus part of the group ring is just the quotient of ZP bracket G by the ideal generated by 1 plus C. So this is the largest quotient on which C acts by -1. And the same for any module. So if I have a module M, then the minus part is what I mod out by 1 plus C times N. That is the largest quotient on which complex conjugation C acts by -1. So this is called the minus side. And now we're ready to state some refinements, and these are due to Kurihara, Burns, and Sano, these precise statements, which is that theta is not just in the annihilator of the class group, but it's in the fitting ideal of the Pointryagin dual of the class group. Okay, and so this Pointryagin dual is important. Actually, it's quite important. So, a more natural question to ask is theta in the fitting ideal of the class group, right? And it was kind of observed by Popescu in the function field setting that this doesn't always hold. And Kurihara kind of came up with examples in the number field setting also where it doesn't hold. So it became apparent after some initial kind of, attempts to refine the conjecture, or the most natural things that theta lives in the fitting ideal of the class group, that strengthening doesn't hold. But if you take the dual, then it, conjecturally initially does hold. As I'll mention in a moment, this implies the Brumer-Stark conjecture, even with the dual here, for a reason I'll explain in 1 second. Now, there's actually a further refinement, and I'll have to explain this, so I won't say much right now, but there's a certain module called a Ritter-WEISS module, which is in some sense a generalization of a class group. Okay, and the conjecture is that the fitting ideal of the Ritter-WEISS module should be exactly generated by theta. And the fact that its principle is reflected in the fact that this nobla, which I haven't defined, that it has a quadratic presentation. In fact, it's defined via a certain specific quadratic presentation. So, so the fact that you can define a sort of a canonical module whose fitting ideal should be theta is quite remarkable and was actually essential for our work. Somehow quadratic presentation seems to be an important feature of our arguments. Okay, so let me say a little bit. I haven't said what this theta is. I haven't said too much about this dual. Let me say a little bit more about that. Okay, so this nabla, as I said, it's a generalization of a class group. It's some G module that's made from class field theory. To give some intuition for it, as you know, sort of class number formulas tend to relate regulators times class numbers to leading values of L functions. So on the purely algebraic side, you'd like to see something that sees not just a class group, but sees a regulator times a class group. And that's the motivation for nabla. Sort of nabla, in some sense, kind of tries to put both of these together. And so that's what you should see as related to the L function rather than just the class group by itself. So the fact that you need some algebraic thing that's a little bit more general in the class group is maybe not surprising. Maybe the thing that's surprising is that you can actually define such a thing. This was done by Ritter and Weiss with the smoothing, that was sort of work of Kurihara, Burns, and Sano, and also Haitian. I had an alternate construction that was important in our work. Okay, so now for our purposes, I'm not going to define nabla. Maybe Mahesh will do that in his lectures. But the property, one of the important properties that it has is that there's a surjective map to the dual of the class group. So that's the way in which I say it's a generalization of the class group. It's a little bit bigger, okay? And the second conjecture now, from the previous slide, you can see that it implies the Brumer-Stark conjecture. Okay, the second conjecture, in case you've forgotten, is this statement here, that the fitting ideal of nabla is precisely generated by theta, okay? Now, if you remember, I said if you have a surjective map of modules, then you have a containment of fitting ideals. So if this is true, if the fitting ideal of nabla is equal to theta, then that implies that theta is contained in the fitting ideal of the Pointryagin dual of the class group, because you have such a surjection. Okay. Now, I've also said that the fitting ideal is contained in the annihilator. So if I have this containment, then I have the containment that theta is contained in the annihilator of the class group dual. Okay. So now I'm getting sort of close to Brumer-Stark. Well, it turns out it's very easy to show that the annihilator of a module and its Pointryagin dual of a finite module and its dual are exactly the same. Okay, so interestingly, it's not true of the fitting ideals, and that's why it's important to have the dual when you're talking about a fitting ideal statement. But the annihilator somehow of the class group and its dual are the same. So of course, as a group, the class group and its Pointryagin dual are isomorphic, but as a G module, they're not. But it turns out the annihilator is still the same. So then I can say if theta is in the annihilator of the dual, then theta is in the annihilator of the module. And that's the Brumer-Stark conjecture. So this statement that the fitting ideal of nabla is equal to theta, you can see it's a refinement. It's quite a strong refinement, actually. It turns out like this by itself is enough to give the higher rank, sort of Rubin conjecture, whereas this statement itself would not give the higher rank statement. So you can see that there is some real strength in this. Okay. Now, an important study, part of the study of the Ritter-Weiss modules that Mahesh and I did is that we can give a cohomological interpretation of the Ritter-Weiss module nabla. So this is important because of the method of proof that we give, which has to do with RIBET'S method, and RIBET'S method is really fundamentally about constructing cohomology classes. So you have to kind of relate cohomology to this Ritter-Weiss module. So what is that? So the cohomological interpretation we gave is that if you want to have a surjection from nabla to a certain module n, and it can work most generally here. Don't need ZP. I could have put a ZP here, but I just put Z bracket 1/2. On the minus side, this is important. This is true on the minus side. Okay, that on the minus side, a surjection from nabla to a module n is equivalent basically to just the existence of a Galois cohomology class valued in that n, and then there's certain local conditions. And in today's talk, I'm going to completely ignore local conditions, and I hope Mahesh in his lectures, when he gives more details on the proof, will describe these local conditions. Okay, and I just want to point out the word surjective here. What is a surjective cohomology class? I think this is non-standard notation. We call a cohomology class surjective if any cocycle representing the class, if every cocycle representing the class has the property that as a function from GF to N, so as a one cocycle, as a function, it's surjective. That is, the image generates n as a T module. Okay, shouldn't say surjective function. I should say, yeah, that the image of that cocycle generates n as a T module. Sorry, as an R mod. Well, what is TR? As a module for the ring you're talking about. In this case, our ring is this. Okay. So as a Z what bracket 1/2 bracket G module, sort of the image of any representing cocycle has to. In other words, what we're saying is there's no submodule of n in which the cohomology class kind of arises from that submodule. Okay. Now, this is kind of a lemma. Actually, sorry. So before I say this theorem on the bottom, let's talk about the top. So what does it mean? So if we want to prove that the fitting ideal of nabla is contained in theta, right, then we can kind of, the previous slide says what we need to do, okay? It suffices to construct any module M on a surjective cohomology class valued in n, okay, satisfying the local conditions, such that the fitting ideal of n is contained in theta, right? Because then the previous, cohomological interpretation of nabla gives us a surjective map from nabla to n, okay? Because that's what the previous slide said, that a map from nabla to n, a surjective map from nabla to n, is the same as giving a surjective cohomology class. And so if you do that, if you have a map from nabla to n that's surjective, and you have the fitting ideal of n is contained in theta, then by the property of fitting ideals, if nabla surjects to n, then the fitting ideal of nabla is contained in theta as well. And so that would give us that fitting ideal of nabla is contained in theta. Now you want an equality, but it turns out it's not too hard to prove that getting an inclusion is enough to get an equality. That is, if you have the fitting ideal of nabla is contained in theta, you can show that that's enough to show the fitting ideal of nabla is equal to theta. Somehow, these are known to be principal ideals. So somehow one is contained in the other, then that means that theta divides, the generator of the fitting ideal of this, as long as you pass to a quotient ring on which these are non-zero divisors. And then from that and some analytic argument using the size, basically, you can determine what the size of nabla is, and sort of, this ring modulo this nabla, the size that is equal to this ring modulo theta, and because of that, you have one divides the other, they have to actually be equal. All right, so I sort of glossed through that proof, but this isn't the depth of the argument somehow. So this was somehow a standard argument in Iwasawa theory when you're trying to prove some characteristic ideal is generated by some L function. It's often known that if you prove an inclusion of one and the other, then you in fact have an equality. So we've kind of whittled away all the layers of this conjecture to now just constructing one cohomology class. That is, we need to construct a module n and a surjective cohomology class valued in that module, satisfying some local conditions and control of the fitting ideal. So sort of those three things. And then we'll sort of get the Brumer-Stark conjecture, in fact, the strong refinement falling out. Okay, so you kind of massaged and reshaped the conjecture one after another. Like, started out as something, how are you ever going to do it? You want to prove the existence of units and abelian extensions of number fields you don't know how to do. We've kind of whittled it away. So now it's just constructing a cohomology class. Okay, but it's still, hard. How do you do that? And so you do that via RIBET'S method. All right, so you have some relationship between L functions. So the L functions that we're dealing with here are theta, our STICKELBERGER element, and the class group has now been replaced by this nabla somehow, right? And you do that by sort of going around a circle a long way. Okay, this is a loop around RIBET here. So if we want to go from L functions to class groups, we start with Eisenstein series. So Eisenstein series are certain specific examples of modular forms. Okay, we're going to be talking about Hilbert modular forms, which I'll describe in a moment. But the point is somehow that Eisenstein series have constant terms that are L functions. So we want to define a certain kind of modular form whose constant term is our theta. And so we'll do that. Now, from Eisenstein series, you can make CUSP forms. Okay, this is very familiar. The first time you ever saw an example of a CUSP form, presumably it was the delta function. And how do you make the delta function? Well, you take two modular forms that are Eisenstein series. Those are things you know how to write down explicitly. You take E4 and E6, and you put them in the same weight. So the least common multiple of 4 and 6 is 12. So you take E4 cubed and E6 squared, and then you take some linear combination of them to cancel out the constant term at the cusp, infinity, and there's only one cusp on SL2Z. So there's only one constant term you have to cancel. You take the linear combination. You know there will be one, whatever the constant terms of E4 and E6 give you. And when you take that linear combination, you get a cusp form, and that's delta, right? And that's the same idea. You take products of Eisenstein series once you have them, and you take the linear combinations or differences, and you cancel the constant terms, and then you get a cusp form, okay? And why do we care about cusp forms? Because cusp forms have irreducible Galois representations associated to them, right? So once you have a cusp form, you can look at its associated Galois representation. And this is where the link between the analytic and algebraic theory happens, right? So in the source, right, you know, these conjectures about L functions are very interesting because they relate something that has an analytic source, that is these L functions made of infinite Euler products, and you take some analytic continuation to another point, and you relate to something algebraic, the valuation of units. So where does the connection happen? It happens here. So you're going from a cusp form which you've constructed analytically, and then you're saying I have a Galois representation that's associated to it, which is saying something algebraic, right? Something about the action of a Galois group. Once you have this Galois representation, if it turns out to be reducible, or if some reduction of a Galois representation is reducible, which is what happens when you have a congruence between an Eisenstein series and a cusp form, which is what we construct, then you have a Galois cohomology class associated that arises, I should say, from that Galois representation. And then you need to make some connection between the Galois cohomology class and the class groups. And I've already described that. I've already said that a surjective map from Nabla is tantamount to an existence of a Galois cohomology class. So I've already sort of explained this in some sense, this last arrow. Okay. So now let me start from the beginning of this loop, but that is, what are the modular forms that show up? So in our case, they're Hilbert modular forms, and I want to describe them. So the proper way to do everything is, adelically, but I'm going to describe them in a much more sort of down-to-earth classical way. So if I have a totally real field of degree n, if its narrow class number happens to be 1, then I can say very simply what a Hilbert modular form is. It's a holomorphic function on n copies of the upper half plane that satisfy a transformation law with respect to the group GL2 plus of OF. And this is just the usual automorphy property. So if I take a matrix A, B, C, D, so what is GL2 plus of OF? So these are matrices in GL2 of OF, the ring of integers of F, that have totally positive determinant. So it means under every real embedding of F, the determinant is positive. Then you can define an action. Okay, so F, the slash action on such functions in weight K, is you do your linear transformation in each variable. So what is A1, B1, C1, D1, etc.? Well, there's n embeddings of F into the real numbers. So that's, for my matrix A, B, C, D, I can take the embedding of this matrix, into each of the n real places, and that gives me matrices in the real numbers AI, BI, CI, DI. Okay, so AI, BI, CI, DI. This is for each I. This is going to be a matrix in GL2 plus of R, or right. So this is just matrices in GL2R with positive determinant. Okay, then sort of this makes sense. It's a linear fractional transformation. This is some element of the upper half plane. So I have n variables in the upper half plane here, and then there's the usual automorphy factor of CZ plus D, and you take the product of them over as I goes from 1 to n. So this is kind of when n equals 1. This is the usual transformation property for a classical modular form for SL2Z. Okay. So now you might notice that, as long as n is greater than 1, you don't have to worry about sort of growth conditions at the cusp. They're kind of automatic when you have a function satisfying this property that's holomorphic on n copies of the upper half plane. Okay. So now we need to be a little bit more general. That is, you need to have level structure. We can't talk about Hilbert modular forms for all of GL2 OF, and just like for the usual classical case, you want to add some levels. So if you add level n, look at matrices that are upper triangular mod n. Okay, so then there's a sort of a condition that that if I have a character of O mod n star, and this is still under the assumption, this definition is still under the assumption that F is narrow class number 1, then a form of Nebel type is chi, where chi is a character of OF mod n star, is just a form that transforms under not all of GL2 plus OF invariantly, but somehow under gamma naught of n invariantly, under all of GL2 OF plus gamma 1 of n invariantly, that is matrices where C is an n and sort of the D is congruent to 1 mod n, and it's invariant under those. And under this bigger subgroup, you have this sort of extra root of unity factor, which is that it transforms by multiplication by a character. So this is sort of a direct generalization. If you use forms with Nebel typus for SL2Z, this is kind of a direct generalization. Now, there's generalizations of all these definitions to the case where the narrow class number of F is not 1. Oops, sorry. Okay. So in that case, a Hilbert modular form will be an H tuple of holomorphic functions rather than just one holomorphic function when the narrow class number is greater than or equal to 1, where H is the narrow class number. And there's sort of each of one of these functions has an invariance property with respect to not GL2 plus OF or not even gamma naught of n, but some sort of modification of that. This is kind of a slightly unnatural definition, and as I mentioned earlier, the much more natural definition is a function of a certain adelic space, sort of quotient of the adels, and that has sort of H components, and that's why if you want to think of it in a classical way, you'll have H different functions. Okay, but one thing I want to mention is that a Hilbert modular form is described by its normalized Fourier coefficients, which is just some data, right, which tells you the Fourier expansion of each of these H functions. So there's this H tuple of functions, which defines your Hilbert modular form. Each of this has a Fourier expansion, and you can sort of package all that information together into a set of what are called normalized Fourier coefficients. And so that is the data for each non-zero integral ideal of F, some complex number, which you define. So these are both, complex numbers, right? And a bunch of sort of constant terms. And these are the constant terms sort of at infinity. These aren't all the constant terms. You just like a normal modular form, when you look at its Fourier expansion, you talk about its constant term at infinity, which is just one number. Now, since you have H functions, each of those has a constant term at infinity. And so you have sort of H of these constant terms at infinity, C lambda. So lambda here is indexed by the narrow class group, is exactly what indexes your H functions. Okay. So those are the Fourier coefficients. And then once you have the notion of these normalized Fourier coefficients, you can put some integral structure on this space of modular forms. You can ask, what are the modular forms, say, with integer Fourier coefficients? Okay, you can call that MK of Z. And it turns out, so this is what you have to prove, that MK of C, that is the space of all modular forms, has as a C basis forms that live in MK of Z. That is, there are integral modular forms with integer Fourier coefficients, whose C span is all of the space of modular forms. And so that makes sense then to define MK of R for a general ring, commutative ring R, to be MK of Z tensored with R, because then if R is equal to C, then it sort of, comes back to the definition you started with. In fact, if C, it's a theorem that somehow if R is any subring of the complex numbers, then MK of R is precisely the set of modular forms with Fourier coefficients living in R. Okay, and then with that definition in half, we can define what we call group ring valued modular forms. Okay, so I guess there's a parenthesis missing here. MK of G, where G is my Galois group of H over F, is that it's the forms with, in MK of Z tensored with ZP bracket G, so what I just called MK of ZP bracket G, such that whenever I apply any character, if I have a character chi of G, then I can apply it, right, to everything in ZP bracket G, and then I just get something in MK of ZP, or maybe finite extension of ZP, where the values of chi live. And then you want that to just be a form of Nebel type chi, okay? And the point is that it's integral, right? So if I didn't have my if I didn't have the integrality here, if I just had CP, then there wouldn't be much to this definition. It would just be a direct sum of MK of chi, that is forms of M type chi. For every chi, I just have a direct sum. This is kind of similar to what I alluded to before. The complex grouping breaks up, or in this case, the CP value grouping would just break up into copies of CP, and then I'd have this condition that the one indexed by character chi has an Nebbin type as chi. So it would just be a direct sum of forms of each Nebbin type as. Okay, the value of this definition is that there's an integrality condition that, as I'm saying, when I package them together into a modular form with coefficients in the grouping, that modular form is integral. So it's saying that the different forms of Nebbin type as chi that you have satisfy congruences, p-adic congruences. Okay, so that's sort of the value of this definition. And it's hard to write down examples of these things, but just like it's hard for me to write down examples of any modular forms. The only modular forms I really know how to write down explicitly are Eisenstein series. I mean, there's some other examples. There's theta series and Poincare series, but generally speaking, the simplest ones that you can actually write down explicitly are Eisenstein series. And why are Eisenstein series important for us? It's because their constant terms are exactly the L functions that you're looking for. And in fact, it's kind of putting the cart before the horse. The reason we came up with this kind of definition, of course, had been studied by others. Wiles and Hida and others have thought about these kinds of modular forms. Is precisely because their constant terms are the L functions that you care about. So we wanted sort of theta to show up as a constant term. So we said, what is the space of modular forms for which theta would be the natural constant term? And so there is an Eisenstein series of weight 1 whose constant term is exactly theta, or theta divided by 2 to the n. Okay, when you're working over ZP where P is odd, this 2 to the n doesn't cause an issue. This is a p-adic unit. And so the constant term is theta, and then the Fourier coefficients are exactly kind of what the usual Eisenstein series Fourier coefficients are. You might think, okay, so if I apply a character chi, then I just get sort of chi of A here, right? And you might expect a norm of A to the k minus 1, the usual thing for Eisenstein series, d to the k minus 1, or sum over all divisors d of n, right? That's what you get in the classical case over q. And you indeed have that here, but of course I'm talking about weight 1, so k is 1, so this term goes away. So you don't have to worry about this in weight 1. And so for each chi, you get chi of A. And so if you put that into a group ring element, that's just the Frobenius associated to A. I should mention, if there's no level here, then this needs to be modified a little bit. So let me not get, that's a technical detail. But in the case where there's a level, then this is fine. Okay. And now, how does RIBET'S method work? Well, I mentioned that you want to take linear combinations of Eisenstein series to get CUSP forms. So what is linear combination that you want to take? So what you want to do is you want to cancel the CUSP form at infinity, the constant term at infinity. So first, let me ignore this VK for a moment. So let's say I had E1, so that's my theta, right? The constant term at infinity is theta, or theta over 2 to the n. So what I want to do is I want to subtract off theta over 2 to the n times some modular form whose constant term is 1 at infinity, okay? So you want to prove that there's some modular form in your space of group ring value modular forms that its constant term 1 at infinity, okay? And you can do that only if you passed a high enough level, it turns out. Okay, so let me, so there's a theorem of my postdoc here at Duke. Sorry, I see that there's a chat message, but my screen is a little messed up, so I can't see the message. Let me try to exit. Oh, I said level. I think I meant to say weight. I apologize. Weight. Yeah, weight k plus 1. So you passed a higher weight. Sorry. I think I said level. I apologize. So you passed a higher weight, and there's a theorem of my postdoc at Duke, Jesse Silliman, that tells you that such an HK plus 1 exists. That is, there exists a modular form of high weight HK plus 1 whose constant terms at infinity are equal to 1. It gives you some other control of constant terms at other cusps, which is important too. And when you do that, then the linear combination, again, if I ignore this VK, the linear combination of constant terms of E1 and this theta over 2 to the n times HK plus 1 is 0, because this has constant term 1 This is constant term theta over 2 to the n, and you've taken exactly a linear combination that cancels constant term. So you look like you get a CUSP form. Now there's an issue there, which is these are in different weight. It doesn't really make sense to talk about E1 minus HK plus 1 because they live in different weight. So that's where this VK comes in. So now you see where this comes in. You need some modular form of weight K, excuse me, such that it has weight K and its constant terms are also 1, but you also don't want to mess up sort of what it looks like. That is, the fact that this was E1 is very important. And so you want VK to be congruent to 1 modulo, say, a high power of P if you're working over a ZP. And so the fact that that exists also is due to Jesse Silliman. So he proved the existence of this VK and this HK. And I should mention that sort of the existence of this VK in a more classical setting, or lambda, in this case, it's just over ZP, the VK is due to Hida. And the existence of this HK in the sort of lambdatic setting is due to Chai. And so what Silliman has done is kind of generalize these theorems of Hida and Chai to the context of these group ring valued modular forms a little bit more general. So he works with modular forms and arbitrary commutative ring and sort of describes the image of the constant term map and shows that you can construct modular forms with the properties that you need. So once you have all that, you have this linear combination such that A, it's a CUSP form because they've canceled the constant terms, infinity at least, and B, there's a congruence. So if I mod out by theta, then somehow this term goes away, right? And then I get F is congruent to E1 times VK. Well, now you can see why I wanted to say, well, VK is highly congruent to 1 modulo P to the n. If theta divides P to the n, then VK is congruent to 1 modulo theta. And so this kind of goes away too, and you get F is congruent to E1. And that's really what you want for the purposes of constructing Galois cohomology classes later. Now let me delete all these scribbles so you can actually read what's there on the slide. The last property that I want to make, or statement I want to make, is that I've only worried about constant terms at infinity. You have to worry about all the constant terms, especially when you're dealing with forms with level. There's more constant terms. And it turns out this construction is not quite right. You have to modify it, and then you get a CUSP form, an honest CUSP form that satisfies F is congruent to E. So E here is just E1 of G. Okay. So once you have this group ring CUSP form, well, what do you get out of it? Well, this congruence gives you a homomorphism from the HECKE algebra. And this is sort of, how, the algebraic thing that you work with now is that I just have a ring homomorphism from the HECKE algebra of the space of CUSP forms. So T, I should say, I don't say what T is here on the slide. T is the HECKE algebra of, and it's important, this is of SK of G, that is the group ring valued modular forms that are CUSP forms. Okay, and you get a homomorphism in which TL goes to 1 plus chi of L, because that's the HECKE eigenvalue at L of the Eisenstein series. So the congruence between F and E1 says that TL under this homomorphism goes to 1 plus chi of L. Okay, and chi is the canonical character. Right, so this is G, the Galois group of H, where F is the quotient of the Galois group of F. Okay, and now I said that CUSP forms have Galois representations associated to them. So now we don't have just one CUSP forms, we have the whole HECKE algebra of the space of CUSP forms. So whereas your Galois representation valued is valued in the total ring of fractions of T, okay? And if you only deal with good HECKE operators, that is, operators away from the level, then your ring T is reduced, and so the total ring of fractions is a product of field. This K is a product of fields, and you get a continuously reducible Galois representation into GL2 of this product of fields that has the usual properties of Galois representations associated to CUSP forms. So it's unramified outside the level and P, okay, and for all prime ideals not equal to P, so, or this should say not dividing P and the level, so slight typo, so this should be P and N, okay. The characteristic polynomial of the Frobenius at such a prime is, the trace, the punchline here is the trace is the HECKE operator at L, TL. Again, the determinant is the usual one, so norm of L to the k minus 1. Oh, this is a type also. There should be a chi of L here. Sort of each form has an Eben type chi. Okay, and then an important property of these Galois representations is that you have control over the local representation. So the restriction to the decomposition group at P is upper triangular, okay, with a quotient that's unramified. This eta is unramified, and there's control over what, you know, eta at Frobenius at P is. Okay, so there's a question from a much earlier slide. Is there a reason to take the negative part of nabla that I specified earlier? Yeah, I mean, the minus side is much easier. So somehow the minus side only sees kind of the sort of the finite algebraic part that is the class group in a sense, because the nabla, as I said, it sees the units and the class group. But on the minus side, the units go away. There's no sort of units on the minus part of and so you don't get sort of transcendental factors coming from sort of regulators of the class groups. You can do sort of, I mean, the regulators coming from units of the extensions. So sort of projecting to the minus side gives you something sort of more purely algebraic and is easier to work with. So that's a nice question, but yeah. Sorry, so let me get back to what I was saying here. So you have this Galois representation. So now we have two different things. We have a homomorphism on the Galois. I'm almost done. so just a couple minutes left. So we have a homomorphism on the HECKE algebra of the space of CUSP forms, and then I have a Galois representation that's sort of valued in GL2 of the total ring of fractions of the HECKE algebra of the space of CUSP forms. And I need to combine them in some way. All right. So again, so here's the homomorphism that I have. So homomorphism on T. It's just that the characteristic Frobenius polynomial Frobenius. Now it factors, remember? So TL, right? So if I take I, the kernel of my homomorphism, then modulo I, since TL goes to 1 plus chi of L, you know, the characteristic polynomial Frobenius is x minus 1 times x minus chi of L, because TL is just 1 plus chi of L, okay? And now you apply this important lemma of Ribet. I mean, Ribet's lemma was done in a more simpler context where we had a DVR. This T is not necessarily a DVR, so it's kind of a generalization of Ribet's lemma. So if you have a reduced complete Noetherian local ring and an ideal, which we're going to take to be our kernel of our homomorphism phi, and you have a Galois representation, which looks like I said, and the characteristic polynomial of this Galois representation factors modulo this ideal, then what Ribet's lemma gives you is a fractional ideal P, okay, of T, and a surjective cohomology class valued. So now you can see where the connection is, how we're producing the surjective cohomology classes that we need for to apply our theorem that a homomorphism from nabla is the existence of a surjective homology class. And now we're sort of putting together all the pieces to round this circle. Okay, so this is Ribet's lemma. So hopefully Mahesh will prove this Ribet's lemma in his lectures. So this is kind of a big sort of gap, you know, which in the summary that I'm giving of the proof is where you get this cohomology class. So now let's say you have a surjective cohomology class valued in B mod IB, where B is a fractional ideal. The last step, or there's two things we need to prove about them. One is that it satisfies the local conditions, which of course I don't have time, so I'm not going to be able to prove. So again, hopefully Mahesh will talk about that in his proof. And in some sense, the local conditions at P, that's the deepest thing kind of in our paper, is how you prove that we have a new method of handling the way of showing that the cohomology class is unramified at P. That's kind of the, you know, for those that were experts in Ribet's method, that's kind of the newest kind of thing that we did in our proof, is how we show it's unramified. It's completely different than what Wiles does, because Wiles' method doesn't work in this context. But let me just kind of sort of finish the proof if you take that for granted, the unramifiedness of the cohomology class. The point is you have a fractional ideal. So the fractional ideal B has the property that it's annihilated. It's a faithful module. So the annihilator of T of B is 0. Okay. And since the fitting ideal is contained in the annihilator, that implies that the fitting ideal over T of B is 0. Okay, because the fitting ideal is contained in the annihilator. But now fitting ideals have base change properties. So this implies that the fitting ideal over T mod I of B mod IB is 0. Okay. And well, what is T mod I? By definition, I was the kernel of some surjective homomorphism from T to ZP bracket ZP modulo theta. So that means that the fitting ideal over ZP bracket G mod theta, B mod I, B is 0. And that's, again, by functorial properties, that's the same as saying that the fitting ideal over ZP bracket G minus of B mod IB is contained in theta. And so now we're done. We've constructed some module, this is my N, B mod IB, whose fitting ideal is contained in theta. We've constructed a surjective cohomology class valued in this module. And by our interpretation of nabla, that means we have a surjective map from nabla to B mod IB. Fitting ideal of B mod IB is contained in theta, so the fitting ideal of nabla is contained in theta. As I explained, that implies the Brumer-Stark conjecture. So this kind of concludes, I apologize, I'm a couple minutes over. This concludes my kind of summary of the proof of the Brumer-Stark conjecture using these techniques. And Mahesh is going to give maybe an entire lecture sort of filling in all the details. Should define nabla. I haven't done that. We should talk about RIBET'S lemma, how you prove the existence of this cohomology class, right? And then secondly, there are local conditions, and the local conditions at P at least, those are the most important. And so we have to talk about how you verify those local conditions. So that's a lot of what needs to be done, but this is kind of the summary of the proof. So I'm going to end my lecture today here. We're going to take a lecture break from talking about Brumer-Stark. Tomorrow, I'm going to talk about sort of refinements and exact formulas for these Brumer-Stark units and applications to Hilbert's 12th problem. And then we're going to get back into more details of the proof when Mahesh picks up the lectures. All right. Thank you very much.
Thank you. Is there any question?
So when we're defining Fourier series, the constant term was a set of complex numbers indicated, indexed by the narrow class group. But then you said the constant term is theta, which is an element of the group ring. So do you mean you have those coefficients and you assembled them into an element of the group ring?
No, so yeah, there's two things going on. So one is that, so the constant term is the same for each lambda. So the constant term, so C lambda was equal to theta for each lambda. Okay. And because my modular forms were valued in the group ring, right, each Fourier coefficient, whether it's a constant term, any other Fourier coefficient, is an element of the group ring.
Okay,
thank you. I should have said for each lambda. Sorry. So yeah, maybe I can go back to that slide. Here. Yep. So this should say, so these Eisenstein series, you're right. There are other Eisenstein series for which the constant term depends on lambda. These Eisenstein series that are written down is the same for all lambda. So this is for all lambda.
Any other question? All right, so let's thank speaker again.